All right, picking up where we left off on the Unit 2 review, we're on number 5. And number 5, again, has a good example where we want to make sure we have the picture set up correctly. We understand what goes where. So number 5, a person stands at the window of a building that is 12.6 meters above level ground. So that's that 12.6 there in blue. An object on the ground, which is 58.5 meters away, so there's our gray, 58.5 meters away, was on a line directly beneath the person. Compute what? An object on the ground, 58 on a line directly beneath the person. I don't know that makes sense to me enough. All I know is I've got a 12.6 meter tall building, and I'm looking at an object that is 58.5 meters away. So let's compute the angle of depression of the person's line of sight to the object. So I've already written that in green. Alpha is the angle from horizontal. Angle of depression is from horizontal in the top of the building, looking down at the object, some object down there. So there it is. There's your object. So we need to figure out what that angle is. And again, what we know, and I think this is the one people have more trouble with, is angle of depression is not that little angle here. In fact, I'll draw it in red because red is wrong. That is not the angle we're working with. The angle we're working with is green, the angle alpha. What we can deduce from that, though, is that if alpha is the horizontal down to my object, I can use that as the same, the alternate interior angle here, alpha here. Because alternate interior angles are equal, now I have an angle whose opposite side is defined and adjacent side is defined. So now let's write that out. Tangent of alpha is the opposite. The ratio is the opposite, so 12.6 over the adjacent, 58.5. We undo the tangent of alpha by taking the tangent inverse of tangent of alpha. We also take that tangent inverse on this side here, on the other side. And when we plug it into our calculators, we get 12.15 degrees. And that makes sense, right? If you think about, you've got almost 60 meters to go here. We've got only 12-ish meters to go up. So that angle isn't a very big angle. I'm standing a really far ways away. I'm only looking up 12 meters. So my angle should be pretty small. So that does check out. And I'm going to do that and box it in. There we go. And we also said, it says compute the angle of depression. Because angle alpha is equal to the angle of depression, I've completed my task. So number 6, hot air balloon. And poof, just like that, I've got some details in there. Spent a lot of time on that hot air balloon. What do you think? Anyways, it is supposed to be a hot air balloon. I know it may not look like one, or one that I would not want to actually be inside of myself. But anyways, we've got some information that we need to account for. So the balloon, I missed that, 650 feet. So here we go. 650 feet above the ground is a hot air balloon that is looking down. Now, the orange and yellow are the exact information pieces given to us. Angle of depression. So looking straight across from the hot air balloon, angle of depression down to one house is 52 degrees. And in another house, angle of depression is 28 degrees. So I've depicted those here with different colors. And again, that's what the information is telling us. The problem is it's not directly useful. What would be directly useful is if we knew maybe these two black angles, 52 and 28. But again, we draw the triangle out as it's shown, and then we use the alternate interior angle definition to draw in the other angle of my triangle to be the angle of elevation from the larger or the farther away object. So again, we'd have two triangles. We have one that goes like this, and one goes like that. So both 650. This one is the farther away one, it's 28 degrees. This one here is the closer one. So you have to look up higher, up in the air, so 52 degrees. We want to know this distance, x, and we want to know this distance, y, which, by the way, that y would be the little guy here. X would actually be the entire distance from the bottom of the balloon to the other observation neighborhood. What we're really being asked for, I'll put it in green, we're going to call that D. D is that distance just simply from one house to another. In order to get that answer, we need to find the distances of x and y, and then we take the distance y and subtract it from that larger distance x, and we get our final answer. So, in question 6, we have the opposite 650 and the adjacent side x, or 650 and y, and we know that that would be the tangent ratios that we're dealing with. And there's the shortcut. I've shown you how to do this before. Multiply both sides by x, and then divide both sides by tan. Or you can take that shortcut method and just replace or switch spots the tangent and the x. So x is equal to 650 over tan 28. So just switching spots, the x, the denominator, and the number on the other side. X is therefore, let's see, with a 28 degree, I believe that's around 1,222. 2.47. Tangent of the other one, 52, is also 650. It's the same hot air balloon, but we have y. So y is going to be equal to 650 tan 52, and that number should come up to about 507.84. So if we know the distance all the way to the first house, or the distance just up to that second house, we can find D. So D, I'll even do it in green. If we take 1222x minus 507, our D answer is approximately 714.64. Our units on all of these were feet. So there we go. That is our second problem. Honestly, you guys, if you have questions 7 and 8, they are very, very similar. I will do another video for that. But if you're getting the hang of things, you can feel confident that if you can do these types of problems, you can do the test problems. So I'll pause here and get one more video for questions 7 and 8.